Welcome back, everyone. It looks like we can start. Welcome back, folks. So for today's class, our whole goal is just to move through section 15.3. We may finish it today, but we're not going to rush it. I'd say wherever we end up today, we're going to be in very good shape for finishing section 15.3, probably pretty early on Thursday's class, which means we'll move into section 15.4, which is wonderful because that will be the last section of the entire course. So congratulations, folks. We are really almost there. We just have to describe how hypothesis testing goes. Well, actually, we already did that. We just need to do a few hypothesis tests so that we see how the problems are going to go in the homework. And then we'll do it again for means instead of proportions. And let's see, what are the announcements? We have quiz number 10. This is the last quiz of the semester as well. Always satisfying to say that. Last assignment, last section. This is the last quiz. It'll be due Thursday, but I do take late quizzes if you don't quite get it on that time. And down below, really far down below, I made a slight change of heart. Quiz 10 is the last quiz officially. And for the extra credit quiz, I decided to make it a real extra credit. It's extra in the sense that this quiz actually goes beyond the course. If you open it up, it's still doing statistics, but this is a large sample confidence interval for comparing two proportions, one population proportion against another. The procedure should look familiar. You're going to take the difference of proportions here. A new standard error, it's not the best form in the world, but that's what happens when you're dealing with two parameters simultaneously. And Z-star is exactly the same. So if you decide to do this extra credit assignment, it has a final due date of December 9th, the same day as the final exam. And you would have to read through this information, absorb it, and apply it on this problem right here, which is a standard kind of, looks like a hypothesis test, or excuse me, confidence interval problem for two proportions. It has the same kind of parts that you would see in a typical confidence interval problem. For example, part E is exactly the same as how it would go, so is part D. The big change on how the standard error looks, for example, on this quiz. If you decide to do this quiz, the way the extra credit will work on this one is it's worth up to 4% extra credit on the final exam. So say, for example, you got most of this right, maybe 75% of this was correct, you'd earn 3 of the 4% towards your final exam score. With the provision that final exam scores can't actually see to 100%. So sometimes students do this extra credit quiz and it actually doesn't help them because they got a perfect grade on the final exam. You very likely got an A either way, so it wouldn't make a whole lot of difference. But sorry for that last part. A final exam is really capped at that 100%. So that's the extra credit quiz. It goes along with the other extra credit assignments and activities. I'd say the easiest extra credit quiz is the course evaluation link, but it's tedious to fill out an entire form. The next hardest one is definitely scoring high on the final exam. It'll replace your minimum scores on exam 1, 2, and 3. So if you had a bad exam, you can really wipe that out by coming back strong on the final. And if and only if you feel like I have extra time, the final's no big deal, I've got this, then try out that extra credit quiz. If you're still getting caught up on your other quizzes, getting caught up on MyStats Lab, then that's the better place to spend your time studying for the final exam. Only think of this as actually really extra in the sense that it's something you would do very, very last, preparing for the final exam. And the information on the finals week, I figured out what I did wrong. I accidentally clicked on that, and it just hides the week. So you learn something new every day. Been using Moodle for like 20 years. But anyways, this is the final exam information that was just suddenly missing on Monday's class. It's officially Monday, December 9, 5:30 p.m. to 7:30 p.m. in this very classroom. There could be other students since they have an 8 to 10 p.m. exam, so I invited them to join us if they didn't want to stay up at night doing their final. But it'll be like an ordinary class that has an exam, just the exam happens to be 2 hours long. And as we get closer to this big break, pretty much on Friday of this week, I'm going to change over to posting more and more information here about studying for the final exam, study guides, and that kind of stuff, just like exams 1, 2, and 3. And that's been a lot of talking so far. Any questions or comments at the moment, folks? Okay, well, we're about ready to start doing some real honest hypothesis testing. The first example of 15.3 was kind of just an initial example, getting used to the ideas of hypothesis testing and the logic behind it. But then after we finished that example one, we went back here. This part right here is all about the conditions of this hypothesis test we're about to describe. Condition one essentially says you need random data. That's what we definitely expected. Condition two is tricky. We'll make a big deal out of it when we apply it. This condition is saying the successes we expect in our sample size of n, when the null hypothesis is true, it has to be bigger than 10, and the failures we expect has to be bigger than 10. So we're not actually using the sample data. That's a really huge change from the confidence interval. Other changes are when we assume the null hypothesis is true, we have a true standard deviation. We drop it down below here on our test statistic z, which we refer to, well, I should say this better. This is a z-score. We just refer to it as the test statistic in this context. So that's the procedure so far. We calculate the test statistic. Then we calculate a p-value, and we'll come back to this table here on how to calculate those p-values. This was just a visual explanation. After we get our p-value out, we go back to our hypotheses. They're to be tested at some significance level alpha that either the problem specifies or the problem will ask you to specify. I think that's what's going to happen in our example too. Once you compare your p-value to whatever significance level alpha the test has been set as, we make a decision based on these two potential outcomes. This is the one where we found evidence the alternative hypothesis is true. This is what the researchers want whenever they do this kind of study. And this is not the best case in the world, but it's still important to know when we just didn't have enough evidence to support the alternative. That's when your p-value is equal to or larger, more likely than the significance level alpha. So that's a lot of information, lots of ideas to tie together. But now we're finally going to apply it in a full example. Any questions first, folks, about any one of those elements in the hypothesis test? Okay, well, we're going to need a calculator out, so let's get this going. And here's how this first question starts. Example 2. It says the Substance Abuse and Mental Health Services Administration conducts surveys on drug use by type of drug and age group. So another set of really serious looking governmental data is probably what this is. Results are published in National Household Survey on Drug Abuse. So you can probably look that up at any time to see some more recent data. According to that publication, we're told 13.6% of 18 to 25-year-olds were current users of marijuana or hashish in year 2000. I'll just paraphrase that to users of marijuana. I'm not sure why they specified that right there. That seems important. Let's just give it some temporary highlighting for the moment and see what's going on in the next part of the problem. So it says next, a recent poll of 1,283 randomly selected 18 to 25-year-olds. So we have lots of really young people. Let's found that sample size. Sample size is 1283. Goes on to say it revealed that 205 currently use marijuana or hashish, however you pronounce that. Let's highlight that right there. This is starting to take shape. The 205 came from the sample of 1,283, but it looks like that's what the success is in this problem. The earlier paragraph said that at 13.6% of those 18 to 25-year-olds were current users in year 2000, and now in a new sample, we have 205 of them. So let's write out here, there is 205 successes, which essentially is saying that this part, current users of marijuana, this is the success in this problem. So they go on to ask next, do the data provide sufficient evidence to conclude that the percentage of 18 to 25-year-olds who currently use marijuana has changed since year 2000? That's a question, right? But one thing that's interesting about these kinds of problems is the alternative hypothesis is the research question. In a really strong sense, this part right here is a statement about HA. We just have to put it together and write down what is the parameter and what is the rest of the alternative hypothesis statement. So if you ever notice there seems to be a question in a problem, oftentimes that's a dead giveaway. They're talking about the alternative hypothesis. So let's pretend we're talking about year 2024. We're wondering if 24 years later, this old value, 13.6% of that age range, being current marijuana users, has changed. I think a lot of people would ask the question, has it gone up? That seems like a more natural question. But this problem is asking for a two-tailed test the moment they said this. We're testing for either direction. Maybe it's gone down. That's pretty optimistic. Maybe it's gone up. That might be more realistic, but they're asking for change in any direction from the old value, 13.6%. That means this 13.6% is P naught, the hypothesized value. So at this point, we're about ready to state our hypotheses. Any questions about the context so far or how we broke it down? Okay, part A for a hypothesis test on a real quiz or exam is worth a little bit more because we're doing two things. We're defining the parameter. Well, we're doing three things really. No, four things. We're defining the parameter. We're defining the null hypothesis, the alternative hypothesis, and then in this problem, we ourselves will choose a level of significance, alpha. So let's start off by the most important thing in this whole problem. The thing we're testing is P, the unknown parameter. We have to describe it using the context. But if we look at these data, these are absolutely categorical data. So we'll say P equals the true proportion of, we have to mention the population at this point. Anyone see what the population should be? Not necessarily, that'd be the successes. Let's put down kind of like a trail of hints. For right here, we want the population, right? But you know what comes from the population? The sample. That's the sample right there. So look where that sample came up first. They're talking about the population now. Anyone see what it would be? Exactly. So if we say all 18 to 25-year-olds, we're talking about the population. So long as I can spell year olds right, there we go. So now we're talking about the population. And then as you said, we need to mention next the successes. So here, excuse me, on this part, this is the success of the problem, but that's just being current users of marijuana or hashish. Again, I'll just paraphrase this to current users, let's just say of THC to make it even more abbreviated. That'll save a little bit of time. So that's the population parameter. I don't know why I did that. I still need more space on this problem. Any questions at all, folks, in indicating that parameter? Okay, there's several elements we have to always hit when we indicate the parameter. If you didn't write the P equals, I wouldn't be too worried about that. It's definitely a good idea because you want to keep P and mu separate in your mind. The act of just writing it down already helps. But we also have to say proportion or percentage somewhere. You don't have to say true proportion. You could say population's proportion or population's percent. That's fine as well. We have to say what the population is, and we have to say what the successes are. So these are the three required elements for a proportion P. But once we get through that, we're ready for this part. Null is H naught. Alternative is HA. We state these by putting not an equals right here, but just a colon. So we're saying H naught is the statement that after the colon, we put down P on both of these. Next thing we'll put in is, let me get a good color to tie this together. Because we're asking if the amount of users or proportion of users has changed, that means this is a two-tailed test, and so we use not equals right here. Might as well say that up here just to be specific. Keep in mind, however, this is pretty tricky when it comes to the null hypothesis. There is always equality right there in this text. Some texts do it a little bit different, but our textbook always puts directly equality in that location, which makes sense because no matter what textbook you're using, the first step is to assume P is actually equal to something. The thing it's going to be equal to is that value up there as a proportion, 0.136. That deserves a special color. Let's go with this blue so it can stand out a little bit better. Let me know if that is not readable though. Does that look all right to folks on the projector? Yeah. Okay, awesome. So that value will go right here. It'll also go right here. So 0.136 goes in those two locations. And now here is the surprising part that's really easy to miss, I'd say. We also want, in this problem, to choose a level of significance. This is something that the people who did the study would have done before they even collected data. So we're imagining that happened. We're just placing the value. Well, placing a value for the significance level alpha can be a little bit tricky, but it's all up to you what you want to put down. Let's pause right here and take a look at some notes where this came up for the very first time, which should have been section 15.1, I believe. Or was it? Hang on, I think it might be in these notes actually. Let's scroll up for just a moment and take a look at our information about alpha. There we go. So we have typical values, 0.10, 0.05, 0.01, which corresponds to being 99% confident, 95% confident, and 90% confident, in other words. So just like in this land, if you want to have really precise and sure information, you go for high confidence. If you're doing hypothesis testing and you decide you need a lot of evidence before you knock down the null hypothesis and accept the alternative, you would use 0.01. That's a high benchmark for evidence. 0.05 is more typical. And 0.10, it's a weird level for alpha, but if it's a low stakes problem, sometimes it's not a bad value to choose. So let's take a quick screenshot here. Hold that thought in your minds and let's go back down. I forgot how long these notes got. There we are at the bottom. So this could happen on a real exam. Choose a level of significance. It's totally up to you, and I'll leave this up to the class now. Any volunteers from the class, either in person or over Zoom, for a level of significance? This is about 18 to 25-year-olds using THC. And if we reject the null hypothesis, there's a good chance that something could happen with public policy. Federal government might put out some PSAs on the radio, something like that, or maybe something more substantial. It could be costly. So, any volunteers for what alpha ought to be in this situation? It seems like we just don't know what would be the best one, right? That's good too, because if you are just totally not sure what a good value is, it might mean the problem doesn't really seem all that impressive or high stakes. It doesn't seem like a big deal. If you just feel like, this is an interesting problem, but I don't care how it goes, pick a 0.05. It's right in the middle. It's a good default value to select. So if you feel like, man, I don't know what to put down, that's a good value to start. Let's go with 0.05. Now that we put it down, we have to stick with it. We're imagining that we are the researchers. We would say what our parameter is. We have to indicate the population. We have to indicate what we're interested in, the successes. We would then define the hypotheses in this way, and we would nail that significance level down. The next step we would do is then and only then we collect the data, see what it looks like by looking at the number of successes, and now conduct the hypothesis test without changing anything here at all. If we make any changes after collecting the data, that's considered one of the major unethical things about statistics. Because we could, say, for example, get a large p-value, larger than 0.05. We won't reject the null hypothesis. But in the past, sometimes people have done this. Wipe out the two-tailed test, make it a left-tailed test, and you can suddenly make it significant. That's unethical. You have to stick with what you said you want to test at the very, very beginning. So let's go back to what it was. We've got a significance level alpha set down. Let's actually say that verbally, because I feel like if this comes up as a quiz question or final exam question, more likely, that would be really confusing right here. So this is the significance level. Alpha. Let's say even more right here. If the p-value is less than alpha, we have evidence in favor of HA. If it's greater than or equals to, that's the bad outcome. We don't have evidence in favor of HA. So we're about ready to start the test. Any questions at all, folks, with the first initial analysis of setting up the parameters, all that fun stuff? Okay, let's check the conditions next. Condition number 1 is a condition about randomness. Simple random sample would be the best kind of sample that we could have indicated here, but they did tell us at least there were 1,283 randomly selected 18 to 25-year-olds. So we could say here, the data, let's say maybe in a better way, the sample was collected randomly. So condition 1 is met. Now we need to be extremely careful in condition 2, because condition 2 is totally different from when you're checking these conditions on a confidence interval. So let's make this a really big deal and say condition, maybe a better way to say this, sorry. Let's say sample size for hypothesis testing So here's how we'll check if our sample size is large enough in this land. And it's hard to know when to stop adding more detail, but I think it's a really tricky part right here. So let's add just a little bit more emphasis. Different from confidence interval condition. Okay, I think that'll help quite a lot. Honestly, this is something I forget too, because it's suddenly just a big random change. The reason it feels that way is because hypothesis testing is a different kind of logic. We assume immediately the null hypothesis is true now. So in the year 2024, the amount of marijuana users is 0.136 or 13.6% for that age range, 18 to 25-year-olds. So we made that assumption immediately if we're doing a hypothesis test. Now we look at our sample size. The expected successes and expected failures has to exceed 10 on both sides. So let's calculate the expected successes when H naught is true is by this formula. We take n times P naught. Not this P. This is the unknown. We don't have a value for it, but we do have a value from this. It came from the historical data in year 2000, I think it was. So we take n times that P naught value. N is at a sample size 1283. So that's multiplying 0.136. That definitely looks like it meets the benchmark, but for the sake of credit, we have to say what this number is. So 1283 times 0.136. So we get 174.488. Now here's a weird thing. Even though it's a decimal number, we keep that decimal number. Seems weird because in the actual sample, you can't have 174.4 successes, right? So the reason we keep the decimal though is we're saying if we repeat this hypothesis test over and over again, the expected successes is just an average. On average, that's how many successes you would get. And even when things can't be integers, if you take the average, even when things can't be decimals, when you go to take an average of something, they are now allowed to be. So this comes out as 174 point, let's just round this to one decimal place, 0.5, which is greater than or equal to 10, making that condition met. Let's highlight, because it's greater than or equal to 10, that condition's met there. Then we just do it all over again. The official formula is to go n times 1 minus P naught, but we've explored a couple times in class, there's really two ways to get that. You can either use this formula here, or you can take the sample size 1283 and just subtract 174.5. Let's go both routes just to see how it works if you decide to go the shortcut. So let's use the full formula first. Sample size is 1283. Oh, sorry, I should say what we're about to calculate. I think I have enough space right here, but let me back off right here and just say what we're calculating on this one. The expected failures when H naught is true is, now we can get started, n times P naught equals 1283 for n. And oh dear, sorry, I'm making a mistake on that one. It's n times 1 minus P naught. Big apologies to anyone using pen today. Sorry for the eraser issues. So sample size n is 1283 multiplied by 1 minus 0.136. Let's throw that into the calculator, get a value out, and then check the shortcut. I think this is like a good sell on doing it the shortcut way, I think. 1283 multiplies 1 minus 0.136. So my expected failures comes out at 1108.5. It only had to be greater than or equal to 10, so we very well meet that benchmark. But like you've noticed, I kind of struggled with that, writing it down twice and then writing it down incorrectly and then fixing it. The second formula is a little bit annoying. So if you like the shortcut, it goes like this. Go 1283, subtract your expected number of successes, 174.5. Get the value, 1108.5, already rounded and ready to go. And that's a great way to calculate it as well. We could say here, or compute n minus expected successes for the same exact result. Okay, well, in the end of the day, after looking at all of this, the conditions are met. And I think I ran out of space to actually say that. Let's see if I can fit it in right here. The conditions are met. I kind of painted myself into a corner on that one. I wouldn't take off points if you didn't say that last part, but whenever you're checking multiple things at once, it's good to give an overall statement at the end. Either conditions are met or they're not met because of some reasons. Okay, so we've got through the condition checking, we got through the hypothesis setting. This is the tough part of statistics because it's all pure context, I would say. Condition checking is a little bit tricky on its own. But now we're up to the fun part. This is the mathy portion where we're just throwing things into formulas and seeing what happens. As we go, we're going to want, well, let's see if we can just maneuver with the screen as it is right now. First things up is the test statistic. Once we get a test statistic, we'll be ready for a p-value. But the test statistic comes with a certain amount of steps. When you see this, it's Z, formula goes p hat, minus the hypothesized value. From your null hypothesis, it's defined as p naught. Then the whole thing is divided by, I'm running out of colors, but let's go with just black for that one. Standard deviation of p hat. So that's the thing we need to calculate. To make it happen, let's grab some values. First up is p hat. I forget the number of successes, so let's scroll up and take a look. We had 205 successes, so that's the numerator. It's divided by the sample size, which was 1283. So we have the sample proportion of successes. 205 divided by 1283. Now recall historically, 13.6% in that age range were THC users. In our sample, it is, wow, about 16%. So it's definitely changed, it looks like. Or has it? We don't really know until we involve the standard deviation, calculate a p-value. In other words, p hat might look impressive, but it's only impressive if the number of standard deviations p hat is away from p naught is large. So that's why we need the standard deviations next. Let's record our result though. 4 decimal places is pretty standard for these, so let's give it 0.1598. Any questions so far, folks, with the p hat portion? Okay, p naught, we can just write it down, but it's always right here from the null hypothesis. So p naught is 0.136, excuse me. And now from this point, we can calculate standard deviation of p hat, the last part. So SD p hat. The way to think about it is, recall how standard error p hat goes. It's almost the same. It's a big square root with a sample size n down below. But the change is, the statistic doesn't go up here at all. We're putting in the true value of the parameter when the null hypothesis is true. So that's what it would look like as a formula. This turns into square root 0.136 for p naught, 1 minus 0.136 again, divide by the sample size n, and that sample size n we can read from p hat over here, 1283. So that should give us a value out. Back into the calculator, depending on how you do it, let's try the order of operations way. I'll work inside out. So it'll be 1 minus 0.136. So we've got that computation. Multiply it by 0.136. So now we have the entire numerator. Divide by 1283. So now we have something with a scientific notation being provided, not an error, though E seems like it could be saying error. We just take this value, hit second, power 2 button right here to access your square root, hit second, enter to throw it, oh, hang on, I messed it up. That didn't work. If you messed it up like me, just hit clear, go second, power 2 button like that. The TI-84, it's easier to just paste in by up arrowing and hitting enter. I think that's the best way to do that. Hit enter again, and that's finally our standard deviation. 0.0096 is what I got. Does that look right to everyone so far? Awesome, let's record the result, 0.0096. And I ran out of colors, but I guess you can still highlight stuff. So that's a great way to color code. Now that we have all this down, we can finally calculate Z. So Z turns into just dumping things in as we see them, going left to right, top to bottom, 0.1598, subtract P naught, which is at 0.136, divide by standard deviation at 0.0096, and you know the standard deviation is actually pretty small. The difference in the numerator looks significant, so it looks like this could be a lot of standard deviations. So let's take a look. In the calculator, definitely you want parentheses if you put it in one step. 0.1589 minus 0.136. Divide by this figure, 0.0096. And we have 2.385 standard deviations. Again, that's quite a lot of standard deviations. If it was around 3 standard deviations, I would say you're rejecting the null hypothesis almost as a guarantee. But this one, it could still be kind of up in the air if we reject or fail to reject. So let's carefully put this in, 0.2385, 2.3854. And just as a reminder on this problem, it's always a good idea to remind yourself, what in the world did we actually calculate? What this is saying is the data, by the data we mean p hat, is 2.3854 standard deviations away from the hypothesized value. We should say what we're referring to when we say that. The hypothesized value of P naught is 0.136. So a lot of standard deviations, it looks like, but we won't know if this is a significant result until we calculate the p-value. But this is good news, though. We got through one major step of hypothesis testing so far. Any questions at all getting to this stage? Okay, so to get the p-value, we definitely need to take another look at what our hypotheses even were. So let me scroll up and just take a fast screenshot and then come back down. Okay, so here's our hypotheses, and as well as our level of significance. We'll move around with that screenshot until we're done with it. Hide that problem for the moment, though. So the major feature about calculating the p-value is you need to know what kind of test you were looking at. If you scroll up on the document on this, it shows the two-tailed, left-tailed, right-tailed test. But let's just reproduce it from scratch here in context with this problem. So that right there means we have a two-tailed test. Just like in chapter 5, sometimes when you're doing p-values, it's a really good idea to just draw the normal model. It can help organize what's going into the calculator, what the logic is of how you're getting the p-value. So here's the picture. Let's hide that for the moment. Seeing is believing, and now we're looking at something. We write n to say it's the normal model, 0 to say the mean is directly at 0, and 1 to mention the standard deviation. So with what we put down, that is mu, and that is sigma. That'll be the last two inputs in the calculator. Next, we look at z. If it's positive, then we're going to go over here and double the area to the right of wherever z was. So I'll place it about right here. Z is 2.3854 standard deviations. And this tail right here is not the whole p-value. We also have a negative z over here, which gives this tail. This is why it's called a two-tailed test. But the logic of how we get the p-value is there is total symmetry under this normal curve. We'll just double this area, and that will actually give us both in the nice way. So because we have a two-tailed test, we will double this area. That means we're using normal CDF in the calculator, which means we should specify the inputs. This would be input 1, lower. It's a lower cutoff. Input 2, upper, is positive 10 power 99. These are always the last two inputs in the calculator. So now we're about ready to say what the p-value is. Let's write out p equals 2 times something. I get in the habit of writing out this step because it's sometimes really easy to forget you're supposed to double something. But if you put this on paper first, huge amounts of protection on making that simple mistake right there. Now you know you're just putting a value there, and you will definitely double it next. You can't help but double it now. So step 1, turn on the calculator. Step 2, hit second bars. We're going down to normal CDF, option 2. Lower updates to the test statistic, 2.3854. Upper value, 10 power 99. Mu and sigma are now set correctly, so this is what your calculator should look like at this stage. Hit enter again, and then again, and we finally have a p-value. Excuse me, no we don't. I already forgot. That's not the p-value at all, right? Because we have to double it. So let me put in 0.00853, just so that there's a paper trail in the notes. And now we'll say p-value equals, and the calculator just go times 2 to double your prior result. And that's our p-value, 0.0171 after rounding to 4 decimal places. 0.0171. That means we did it, folks. We now have a p-value. It turns out, yeah, 2 standard deviations, 2.5 almost, is pretty significant on a two-tailed test. Or is it? You know, it just depends on what we decided the significance level alpha was. As a class, we didn't really have a strong feeling one way or another, so we selected a default value, 0.05. We're about ready to give a practical conclusion using the context, but there's a nice thing we should say right here before we go to give that conclusion. Let's say, based on the results we have, since the p-value equals 0.0171, compare that against alpha. It's smaller, so we have less than 0.05, which is equal to alpha. We reject H naught. So that's gone from our consideration. The best evidence we have about the population is that this is now true. P is not equal to 0.136. By what we calculated, p hat, we should say it's higher, but to really give an honest estimate, it's a confidence interval at this point. So let's now go on to the next step, but maybe for the purpose of what part D was asking, calculate the p-value. That would be your answer right there. What we wrote down below is just an organizing thought for going into the next part. Any questions at all, folks, before we give that conclusion? Okay, I want to also mention, notice if we did decide 0.01, this would have been a greater than or equal to, and our conclusion would have been totally different. We would have said, this study does not provide evidence that this is true. But we do have that evidence, so let's go and see what P was. Okay, so we've got our parameter down. We have our hypotheses down there as well for easy reference. We have eliminated the null hypothesis, and now we are in favor of this one. So we'll say that this study provides significant statistical evidence that Now, we go down here and just read out what this statement says. So I get the colors going, there we go. We have significant statistical evidence that the true proportion, or you could say percentage here again, like we've mentioned, of all 18 to 25-year-olds that are current users of THC. So we mentioned P, we can now say is not equal to, just verbatim writing down what the symbol represents. Let me first fix that part right there. THC is not equal to the hypothesized value, 0.136. So finally, that is our practical conclusion, but we really have a lot to say about that as far as practical conclusion, that whole statement goes. For example, it's practical in the sense that we didn't give a conclusion, except HAP not equal 0.136. That's something we can't say. We have to say what we really mean by that. But the trouble with this kind of thing is, if this is a real federal study, and now you're called in front of a Senate hearing committee to explain the results, and you tell them, yes, we have significant evidence that this age range does not have 13.6% marijuana users. It's different than that number. Everybody's now going to probably tear you apart, right? Because their next question is, well, what is it? Did it go up or down? You might say, it went up. I have 0.1598 for the statistic. But then they're going to say, well, what is your estimate for P then? P hat is not a good estimate at all because it has no error tied in with that estimate. You would have to give the full confidence interval. So those whole collection of statements are just a reminder that when it comes to hypothesis testing, it is a powerful procedure, but it never exists in isolation. In fact, let's end this problem right here, but make a couple more comments. This is the overall test for a difference from P naught equals 0.136. So after you do the overall test and it came out significant, we do the following. Since we have significant statistical evidence, a follow-up test, well, let's not call it a test, a follow-up procedure is a confidence interval for P, the same parameter once again, at C equals some percent, excuse me, confidence. So this part is also actually really touchy as well. You can't just give any level of confidence in your confidence interval. It has to be a specific value. It comes from this up here. It will be a 5% confidence interval, but if you have alpha set to 0.05, and now you're doing a follow-up analysis or some extra procedure, your confidence level has to be at, excuse me, 95% confidence. So whatever the confidence value is here as a percentage has to add up with this as a percentage, 5%, to give a value of 1. Or both as decimals, they have to total to +1. So that's what the follow-up test would look like. And now we would say two things. The proportion of THC users has gone up. It is now within this range. And when we give that range, the lower and upper value of the confidence interval would both be bigger than 0.136. Well, any questions at all, folks, with running through that full hypothesis test? Okay, well, I have a question for the class then. we're getting pretty close to the final exam. Should we do the follow-up procedure, running through the confidence interval for the sake of just a mini review? Or would you like to proceed to the next problem? Totally up to the class this time. Confidence interval review or example 3? Review? Okay, let's give that a try. So now we're actually doing that follow-up analysis. Let's call this example 2. Let me just double check it is example 2. Okay, yeah, let's call this example 2, follow-up analysis. Let's also call it really what it is and more honestly. Final exam review question. In the final exam, we'll certainly have to give a confidence interval for a proportion. We just said we're giving a 95% confidence interval. Let's start then by just writing down the formula. A 95% confidence interval for P is, first we take P hat, add and subtract, a critical number Z star. Then we multiply that by, the standard error of P hat. So I think we've already got P hat somewhere on the notes. Let's double check. P hat is 0.1598. Sorry for the scrolling on this problem. It got pretty large after a while. 0.1538. So that's our value for P hat. Now, when it comes to getting Z star, it's a table lookup. Let's check chapter 13. It gives Z star equals 1.9600, or just 1.96 if you prefer. So we've got that value down. So we'll go P hat, we already put in the figure, plus or minus Z star, which is 1.96. Last thing we have to put in is standard error. So it's computed right here. Standard error P hat goes like this. It's a square root with a sample size in the denominator. I have forgotten the sample size. I think it was like 1283. Yes, so that's our sample size, 1283. In the numerator, we put in P hat. So it's going to be 0.1538, 1 minus 0.1538. So all this gets jammed into the calculator. Let's give this another try. In the all-in-one approach, hit second power 2 button, type in 0.1583. Oh, hang on, 38. Then 1 minus the same figure. Then immediately hit division by 1283. And we have, this is a standard error, 0.0101 if you're rounding to 4 places. Double checking, let's see here. 0.0101. Does that look right to folks so far? Okay, so that's what goes into this position for standard error. We're going to multiply by 0.0101. So all this work is going to give us a confidence interval for P. We already have a significant hypothesis test, which means the lower bound right here had better be bigger than 0.136. So let's see what really happens. So we're on this line right here. Type that into the calculator. 0.1538 minus the 1.96. 0.0101. That's just a funny looking number to look at. Put that back. There we go. And our lower bound is 0.134 at a little bit more. Let's double check. That's not what I expected. That is actually below that value. We did 95 confidence, 0.196, 0.0101. Maybe I rounded a little too much. It was really a little bit more. Let me check with the rounding on this one. 0.1538. Then I'm going to go minus 1.96. And I was expecting something bigger than P0. That didn't happen. So let me try putting in more decimal places on this and see what happens. This is the entire standard error right here. So I'm going to go parenthesis, up arrow to, no, hang on, it was that one right there. That's our entire standard error. Let's see what that one comes out as. 0.13405, still not what I was expecting. That is really odd. Well, let me just record the result. I might have to come back to this problem and see what went wrong on this. But I've got a 0.134 on the lower end. Now let's go up to the upper end. I'm just going to move over to the left here and throw in a plus in that location. So we've got 0.1735, 0.1735. Or I should round to the same amounts. That looks kind of weird with different rounding. I'll round this one to 3 places as well. 0.174. Yeah, go ahead.
It's just you have to do the same as you had in the right?
Yes, it is. Did we get that down wrong?
I have 0.15.
That must have been it. Yeah, let's get that revised value. Thanks for spotting that. 0.1598. That would make the change. Okay, let's try this once again. 0.1598. Thanks for spotting that. Good eye. Since that was my mistake, I'm pretty sure that's going to be invisible to me until someone pointed it out. So now with the better values, let's see what happens this time. Like I just want to clear all that out, start fresh. 0.1598, then minus 1.96. Put it in parentheses, and I'll use the rounded value again, 0.0101. This time, the lower value is 0.140. Hey, that means that's good. That is bigger than the 0.136. So finally, the claim we made is actually coming out true. That's always kind of satisfying and really uncomfortable when it doesn't happen the way you expect. Usually it means there's some weird error somewhere. For me, it was miscopying something. I was never going to detect that. So let's go back to the calculator, up arrow twice. Select that, change to plus in the middle. And the upper value is at 0.17. Well, if we round to 3 places, this would be a 0.180. Okay, so double checking one more time. Hypothesized value is 0.136. We have significant statistical evidence that our parameter is different. More specifically, we have significant, or let's say more specifically, this is a confidence interval. We have 95% confidence the true, forgot the highlighting, we'll just smack that with the highlighter. The true proportion, I'll abbreviate this to say of THC users in this age range is between, because I said proportion, I'll keep it at 4.140. If you prefer the percentage, 14.0% is a great way to indicate this, and 0.180. So now we're saying a lot more. The original test was a two-tailed test, so we were testing for any difference, and it came out significant. So in the follow-up analysis, we took the significance level alpha at 0.05, constructed a 95% confidence interval, and now this is giving even more information. The confidence interval shows us that, yes, it has changed from 0.136 and more information, it's larger. Not much larger on the lower end, but on the upper end, it could be quite a bit larger, almost 5%. Well, we did it, folks. We did the complete hypothesis test, and this is now a more real, honest statistical problem. A follow-up analysis is almost a guarantee if you reject the null hypothesis with this kind of test. And the really good news is, if it was a two-tailed test like this one was, so that two-tailed test here, the confidence interval analysis always gives the exact same conclusions. Almost looked like it didn't, but we got the right value for p hat put in to save the problem. Well, any last questions, folks, with getting through this one? Okay, well, we've got about 10 more minutes. Next problem looks like we're dealing with teens and distracted driving. I don't know where all the problems from teenagers are coming from. I think it was the old textbook, was a female statistician and a mother, so a lot of these kind of questions came into the notes. I think this is going to be a tough one to do in about 10 minutes. How about, before we call it a day, let's do the hard part and just define the parameter. Does that sound all right to folks? Okay, so the parameter is always touchy with these kinds of things. We get more practice with it once we're now doing this with hypothesis testing, because this goes the exact same way as it would have in chapter 13 for a confidence interval. First thing we need to do is carefully read this context. The paper, Teens and Distracted Driving, reported that in a representative sample of 283 American teens aged 16 to 17, I started driving at 15. Idaho's a weird state. So we have a sample size of 283 American teenagers. There were 74 who indicated they had sent a text message while driving. I'm just lucky I didn't have a cell phone at that age. This looks like it's the successes in the problem, the thing that they're interested in the most. That's what the distracting driving would be referring to. So let's highlight that there and say, this is 74 successes. So sending a text message while driving. Now, the second part here looks like it's a question, so it's a statement about the alternative hypothesis. Does these data provide evidence that more than a quarter of Americans in that age range have sent a text message while driving? We'll test the appropriate hypotheses, and this one's going to be at a 0.01 level of significance. So we're going for high level of data before we say something about the teenagers being distracted. So we know what the success is. To really get the parameter down, we also need to know the population. Let's start by saying P equals. You could say true proportion, but let's change it up for the folks who'd rather go this way. This is really just a style choice, up to you. I'll say population proportion of all. At this stage, we put down what the population is. Any volunteers for the last parts? Absolutely. So we'll say of all 16 to 17-year-olds, that. Now when we go beyond that, we're mentioning what the successes are. Exactly, that text while driving. Actually, this is kind of a fast one to write down. That text while driving. So we got it, folks. That's the hard part of the problem for sure, getting the parameter down. The next things we would do is write down the null hypothesis, the alternative hypothesis. They gave us that as a level of significance, so it's a really good call for these kinds of problems. Put this on the same line as your hypotheses, so it's a reminder to come back to this when you get your p-value. It's not a requirement, but it's a pretty standard way to set all of your hypotheses: the null, the alternative, and the significance level. This one's going to have a p here, a p here. Equality always goes here, but anyone see what kind of test this one's going to come out as? Two-tailed, left tail, or right tail? Good call. This one's definitely right tail. comes from that right there when it said more than. So we go greater than. Actually, I think we should use a different color for that. That's super tricky because it's like one letter that's choosing the type of test. More than, I guess that's not a letter, that's a word, and it's actually two words. But anyways, that indicates a greater than. So we have a right-tailed test. So we have a greater than that goes right here. And then it says more than a quarter. That's a really rude way to set up information like this, but it did give us P naught. If it says a quarter, P naught is 0.25. Kind of a weird way to indicate these kinds of problems, but watch out for that when it does come up. It's rare, it's a bad exam situation, but it could be quizzes in my stats lab that have wording that can go like that. So we went a little bit beyond, we went beyond the parameter. Now we have our hypotheses. 0.25 would go here and here. I don't want to go too far beyond this. I think this is a good stopping point for us. When we come back, we'll remind ourselves of the context and then run through this hypothesis test as well. Any last questions at all, folks, on setting up these hypotheses? Okay, well, have a great night, everyone. Thursday will be our last class, and then we'll take our last class. We'll take our last class before our break. Then we'll come back on December 2nd, finish off some last concepts, and fully just review on the 4th and the 5th. Well, take care, folks. I'll see you all in Thursday's class.
That's next Monday, right?
Yeah, it'll be on the December 9th, yeah. And pretty much this weekend, starting on Friday, I'm gonna turn over to start putting in the review information to help out with the final exam review. Yep, have a good one. Oh, I have a couple things for you, Brandy. Sorry. There you go. Should have. Give that to the sir.
That's okay, thank you.
You bet.
I just started more for that job.